Hi, everyone, and welcome back to the assessment of the ARK Invest Big Ideas of the Academic Insight series. Today, we have Dr. Joe Littlejohn. Joe, can you introduce yourself and let everyone know what you do?
Hi, I'm Joe Littlejohn. I am assistant professor of urology at Penn State Hershey Medical Center. I am the vice chair of diversity there. I am also the telehealth director at Penn State, and have a company by the name of Linkbox Solutions LLC, helps with HPI acquisition software. That's who I am.
Yes, very impressive. So I know we talked a little bit about the precision therapy and the molecular cancer diagnostic idea. Can you kind of give me some insight and break it down to what it is? Because this is uncharted territory for me. So you need to help me out a little bit.
Absolutely, yeah. So let's just think about like the initial way medications were designed. They were to treat things in a population scenario. So you have the human race and you want to lower blood pressure. So they look for things that could lower blood pressure in general for human beings. Then we've discovered that there are certain subsets of individuals that respond to certain treatments better than others. And that is getting a little bit more specific. And then there's a third layer. The third layer would be taking an individual and saying, for this particular individual, which medication would work the best? And that's when you get to a very precise way of treating that individual. And that's an example of precision therapy. So before, in the 90s, let's say, prior to that, we would treat people based on that scenario. However, now we've become a little bit more precise. After October 1st of 1990, they started the Human Genome Project, and their goal was to sequence a human being's genetic material. And from that point, what they did is they accomplished that goal in 2003. Following that, over the next decades, they have gotten to the point where now they can take any individuals. They could take your or my genetic material and sequence it in a matter of hours. And the price has obviously come down, making this a more accessible situation. So theoretically, now they could take my specific set of genes and predict what medications or what treatments or what therapies would work best for me. And that's where we talk about precision therapy. Where this is being utilized these days is mainly in the cancer realm. Within cancer, there are different genes that we've known about for years, like BRCA2, HERS, things of that nature, where they can look at these genes and then determine what chemotherapeutics would work best based on the characteristics of genes present in that particular patient. Now, we're starting to move over to the realm of molecular diagnostics, and that kind of is also utilized in the realm of cancer. And what that does is it looks at the genetics of the tumor itself. So tumor genetics are a little bit different than the standard genome that would be in the person's tissues. The cancer has to have developed certain characteristics in order to become a cancer, right? So when in normal cells, when there's damage to tissues, the cells have something called contact inhibition. That means when they grow back or heal and they touch each other, they stop growing. Well, there has to be a mutation which causes the loss of this contact inhibition in cancers. And then the cancer cells touch and continue to grow. That multiplication makes them a tumor, an abnormal growth of cells. Well, then those cells have to do other things, like to be able to break off and escape their local environment, that's another set of genes. They have to be able to get into the lymphatic system or the blood system and spread and implant somewhere new. That's another set of genes. They have to be able to develop host, neoangiogenesis, where new blood vessels supply them and allow them to grow in these other places. Another set of genes. So all of these genetic mutations are around, and the molecular diagnostics is able to look at the genes associated with the cancer itself. And that can help with, certainly helpful in prognosis, how aggressive a cancer may be. So that's pretty much what those two topics are about.
Yes, very interesting. Very interesting. So whenever we're looking at, the future of technology, how long do you think it's going to take for us to get kind of wide adoption of these technologies? And because I know me and you talk a lot about D.A.T.A. What's D.A.T.A's kind of role in all of this?
Yeah, I think it's a very exciting time. I think things have been, even in the standard way of doing things, there's been this sort of sharing of information. I feel like there's this thing called REDCap, where data is pooled amongst different institutions and academic centers. So I think inside of the standard way of doing things and inside D.A.T.A, there's this parallel action going on that mimics each other and is synergistic. I think it just needs to come together in a way where each side understands the other side. So what can happen from a DeFi standpoint is, I think you can get new money available to research things that money isn't typically available for. So you just have to name the project. There are already researchers interested in that project. They just can't get funding because there are not many funding sources. Their funding sources can tend to be motivated by the market, in a sense, where if there's a disease that is widespread and affects a lot of people, well, there's going to be money for that. But there are some diseases and projects and things that people are interested in that really don't have a lot of individuals that are affected by them. And then in those situations, those things tend not to be funded. But there might be interest in a subgroup or a community that are really interested in this disease. And I think D.A.T.A allows a community to get together and develop, monies that can be offered as grants to institutions. And once there's a grant available at these academic institutions, the research can be done, and there could be parameters stated, like we will need the data to go into this pool and this D.A.T.A data treasury or whatever, what have you. And that could be part of the stipulation. Instead of using REDCap, you're going to use this other D.A.T.A sort of data treasury, and that kind of thing. It would be a piece of cake to get that stimulated. And I think all of these things that haven't been traditionally funded would get funded.
So do you foresee any kind of regulatory barriers on this decentralized science type approach? And that's one of the questions I've always had.
Well, as long as the health information is protected, I think we have the technologies to sort of de-identify data, utilize aggregate data. And as long as the standard approaches for protecting the privacy of the individuals involved, I don't see many regulatory restrictions with anything that way.
Okay. So is there anything else you would like to add on this topic?
Well, no, again, just I think it's a really exciting time. I think that there's a lot to be done. I think there's a lot of synergy. I think the academic community would be welcoming DeSci with open arms, as long as there's funding for their pet projects.
All right, Dr. Littlejohn, thank you. Thank you for your time. Where can people find you?
People can find me, they could find me on LinkedIn. I think that's probably the best location they can find me.
All right, thanks a lot. So thank
All
you
right.
once again, and for everyone else, until next time.
All right, thank you.